Alrighty, so today we'll start talking about singly linked lists, but I do have some wrap up about selection sort, insertion sort. I do have one exercise for you as well. Credit to Ben, but he doesn't seem to be here today. Maybe not yet, but we'll talk about that exercise, which he asked last time. All right, so let's do some very quick reminder, and then we'll get to the recap about from last time, and then we'll do that exercise together. Okay. All right, so for your assignment number 2, it's going to be about, sorry, let me just fix this very quickly. There we go. Okay, your assignment number 2 is going to be about singly linked lists, which we will start talking about today and definitely dive into more details on Thursday. But once you receive it, you can definitely get started as soon as you can. Assignment number 1 solution, if you got any trouble understanding each part, any part, let me know, and then we can go over. And split array harder, I'll wait for just a few more days, maybe around the end of the week or around the weekend, I'm going to give you guys the solution. You can take a look. Right, about the notes template, I already mentioned, so for those of you who need it, it's on the lecture site, right, before the lecture. And office hour and also TA contact information, consistent, right? If you need help, don't hesitate to reach out. Any question about the course? Okay, and also sometime next week, you can also expect programming test number 1 guide to be released and some practice question as well. Sometime next week. I'll talk about it once it's released. But for this week, you can focus more on assignment number 1 and assignment number 2. That'll be the best prep for programming test 1. Let's now do some very quick recap from last time, which will help us solve that exercise I have in a moment. So last time we basically spoke about different sorting orders, right? We got 4 different possibilities over here. For each one of them, you want to make sure you understand the precise mathematical definition for what it really means. So when you're designing an algorithm, any order is possible. Of course, you're going to adjust the specifics of your algorithm accordingly, according to the sorted order. And we spoke about how you can relate just 2 possible sorting orders over here. And the relationship we have over here is a proper subset. So whenever you see a proper subset, that means you are able to find a weakness in the strictly larger set that does not belong to the strictly smaller set. Just always keep in mind that principle. So if you run into a similar scenario that you got to justify, that's the pattern to go for, all right, about the proper subset, right? You can definitely try different combination of the sorting orders to figure out what the answer should be. Right, and then we talk about selection sort, insertion sort, and I may not dive into complete repetition about each one of them. You can definitely refer to the lecture recording from last week, but let me just mention enough detail for us to solve the exercise today, right? So let's say this. For selection sort, you gotta really watch out for, well, first of all, for insertion sort and selection sort, they follow the same principle. How many steps will there be? It depends on what will be the ultimate size of the sorted area we want to build. And the sorted area size will just be the input size, n. All right, so that's something number 1. Number 2, the selection process for selection sort is going to decrease in terms of its cost. So the first selection is going to be the most expensive. And the last one here is going to be the least expensive or the cheapest. Right? That's a very important fact about selection sort. On the other hand, for insertion sort, we still have roughly about n steps. Of course, you can start with the empty or one single element sorted area. It doesn't really matter conceptually. It will just end up being the same asymptotically. And the insertions that we have, rather than having decreasing cost like in selections, but now for insertion, it's going to be increasing cost. Yes, increasing cost. Because for the very first insertion, you just insert it into the sorted area of one element. So the worst case will be shift one element to the right by 1 position. And at the end, let's say when you got n-1 sorted area, in that way, what will be the worst case? If the one you kind of choose from here, or you want to insert it into in the beginning, and then you got to shift all the n elements to the right by 1 position, that'll be the most expensive insertion, right? Just remember, the insertion will be increasing cost. Right, so that's about insertion sort. And then we also talk about this piece of code over here about selection sort and how we can derive its asymptotic upper bound without even having to understand the logic. So the two most important lessons we learned from last time. Number one, without having the code, as long as you can have enough visual sketch that can accurately describe the critical steps of your algorithm, you will be able to derive the asymptotic upper bound quite accurately without the code. Lesson number two, even given the piece of code as the potential algorithm, you don't necessarily have to understand logic first in order to derive the asymptotic upper bound, which is what we did. Right? So these are the two very important lessons, not just for the two sorting algorithm we're talking about, but just in general. And of course, the exercise for you guys will be, you have to maybe derive the asymptotic upper bound for insertion sort, and also try to trace these two algorithms to make sure you understand how they work. All right? So these are possible coverage for your upcoming written test and also for the exam. So, but they're very good for your learning. So that's why they're covered. Right? Just make sure you spend some time tracing the algorithm both on the paper and also on Eclipse. Right? They're both going to be beneficial for understanding. I'll leave you guys for that exercise. All right, so that's about what we covered last time. Any questions for last time? All right, I don't think Ben is here just yet, right? Okay, too bad. Okay, let's now talk about the exercise inspired by Ben. Maybe Brian, you were part of it, I guess, right? Okay, that's good. Okay, let's talk about it, all right? Which I like. You know, that's kind of give us some nice stimuli, you know, for our brain. All right, guys, here's an exercise. I kind of put it in a format that's going to help you also get an idea how you're going to be asked questions specifically for the final exam. Right? So let's take a look. So to really, in the interest of time, I'm going to explain to you what the problem is, and then I'll let you guys take 1 minute to think about it, and then I'll just take a very simple survey about what you think the answer will be. So there are 3 parts of the question, which I'll explain. I only need a survey on part A, which is the easy part. For part B and part C, I'm going to give you the answer and walk them through. Okay. All right, so this will be a setup for the question. So we're going to recall the detail for insertion sort. We know that the very first insertion is the cheapest, and the last insertion will be the most expensive. So the costs are increasing. Symmetrically, for selection sort, the selections are decreasing. All right, so based on this is what we want to do. Why don't we say we take the best out of the two sorting algorithm to say, since the cost for insertions is actually increasing, and since the cost for selections are decreasing. So the idea would be, why don't we try to do insertions while it is still reasonably low? And we try to do selection while it is becoming reasonably, like relatively cheaper. Right? So we're going to do maybe the first half insertion only and do the second half selection only. That's basically what you guys were wondering, right? Just want to make sure. So that's kind of the intuition. All right? So here's the idea. We want to have a new sorting algorithm which somehow is going to combine insertion sort and selection sort together. Let's say we assume there is an even number of elements in the array. So n divided by 2 can give you a whole number. Okay? So let's say we're going to perform insertion sort for the very first half of the input array. And then we're going to perform selection sort for the second half of the array. The idea would be, again, we want to get insertions done while it is cheap. And we want to get selections done while it's decreasingly expensive. Right? That's the idea. All right, and then the question over here is like this. So we got 3 parts of the question. What I presented over here is part A. Yes or no? Will this new algorithm perform better than the original selection or insertion sort n squared? Will it perform better? That's part A. All right. Part B, justify your answer. Part C, which is also very important, which I didn't think about originally, but one of your fellow students in the morning session reminded me. Okay, part C. So part B is to justify your answer, whether it's a yes or no. And part C, does this new algorithm always work for any arbitrary array? Or there should be certain organization of the element that we should really assume to make it work. right? That's part C, which is slightly more challenging. But we'll worry about part A and part B first. Any assumption on the input structure. And while you're thinking about it, I want to make a little more annotation for you to really see what the problem is. So let's say we start with the array with n unsorted elements. And then we want to somehow to go from zero sorted element all the way to half sorted elements, right? So for this part here, we're going to do insertions. So we're going to do about n divided by 2, half insertions. And then eventually we want to grow the sorted area from n divided by 2 all the way to n, the other half. That part over there we want to do for selections. Overall, we'll still have n steps. It's just the first n divided by 2 step, we're going to do insertion. The second half, we do selection, right? You got to be very clear what we are asking over here, because there's no code here, right? Guys, take 1 minute to think about your answer. You can even think about B and C. Okay. Yeah, give you guys enough time, and then I'll go over the answer. Okay, another 30 seconds. Okay, just one more moment, and then I'll do a simple survey. Already, okay, so for those of you who think the new algorithm combining insertion and selection will perform better, I mean asymptotically better than n squared, raise your hand. Oh, you guys are equally good. It's morning. Good. Okay, nobody thought it's going to be better, right? Okay, what about worse? Anybody think that's going to be worse? I meant maybe it will be n squared log n or maybe n cubed. Nobody think that's worse? So I guess all of you think that's going to be equally the same, right? The performance. Okay? I think you guys got part A right. All right, that's good. So part A is, will this algorithm perform better? No. It will end up being still n squared somehow. But part B and part C are the more important parts to get right. First of all, no. Still n squared. And part B, how do we justify? Part B is not too bad as long as you know the progression of the cost for the insertion. We know that for both insertion sort and selection sort, the selection or the insertion themselves are going to dominate the running time for all the lower terms. So let's only consider selections and insertions to figure out the running time. So let's say for this part over here, about the insertion, right? We're going to figure out this one here. The first insertion will be the cheapest, just 1. And then 2, all the way to the last insertion is going to be roughly about half size of the array, right? We'll only do that, okay? And divided by 2. On the other hand, for selection sort, for the other half, the first selection is going to be the most expensive one. We're going to select basically the minimum from the half of the array that's unsorted still. So that one there is going to be, the first selection will be n divided by 2 plus n divided by 2 minus 1 plus all the way to 1. Both of them are arithmetic sequences, right? Let's now take a look. And you can think about this one here is the first insertion. And this will be the last insertion. And this one here will be the first selection. And this will be the last selection, right? And then let's now sum them up very quickly, right? It's a arithmetic sequence. It's going to be something divided by 2. The beginning term plus the end term. 1 plus n divided by 2 times how many terms do we have? N divided by 2, right? And this will be enough to show, so you can see n times n will be n squared. Everything else is just lower or multiplicative constant. They can be dropped. So we can conclude that this is big O of n squared for the first n divided by 2 steps. And this one here, the insertion part will be something very similar. Okay, I'll just write it down. So, except that the common difference over here is actually -1 as opposed to +1, right? So this one here also, it will be something divided by 2. The beginning term is n divided by 2 plus the n term plus 1, right? Multiplied by, how many terms do we have? From n divided by 2 down all the way down to 1. Also n divided by 2, right? Just half. All right, similarly, you can see n multiplied by n, highest term. Everything else can be dropped. Big O of n squared. So if we try to sum them up together, big O of n squared plus n squared, and this will be the insertion, this will be selection. We still get n squared. Okay, does not improve, also does not make it worse, just the same. Which means you can feel free to modify the code I gave to you and do it like this way. Doesn't really matter. Okay, it just be the same. Some variants to mention to you very quickly, you can also think about. Okay, and then I'll talk about part C. So here we are basically talking about just divide the steps into half and half. Would it work, for example, let's say I do the first half steps as selection and do the second half step as insertion? One variant. Second variance. Let's say rather than saying I'll do n divided by 2, about half of insertion and half selection. What about this? I would say I will do about 2/3 of insertion, and I will do about 1/3 of selection. Would it improve? Right? So these are the variants you want to work out mathematically. It should be quite straightforward to show. Right? Remember those variants and then give it a try. All right, guys, part C. All right. Let me dive directly into the conclusion, right, to save time. But you got to think about it. It turns out this sorting algorithm will work only if the input satisfies certain structural constraint, which is kind of interesting to observe. All right. I'll give you some example. Let's say if you have the array let me give you one example that's not going to work. Okay, let's say here we got 2, 1, 7, 3, 4, 0. I know that halfway is about here. Right? Over here. So what's going to be the outcome after the first 3? So we're going to do 3 steps for insertion. Right? What's going to be after the first 3 steps of insertion? This part of the array will be sorted, which will be 1, 2, 7. Agree? Okay. So I'm just going to do that, and then after the insertions, which will be 3 of them. That one there is going to give me, let's say, 1, 2, 7. That part is sorted, and then 3, 4, 0 remain the same. Okay? That's a halfway. So you can think about, we started with completely unsorted, and then we got this part sorted, and this part still unsorted. Now, if we try to complete the rest by selection sort, are we going to get something that's really sorted overall? You guys already can see, right? Okay, let's now complete it. And that one there, if I try another 3 selections, think about what's going to happen. I'm going to choose the minimum from here, which is going to be 0. And then I'm going to append it to the end. That's going to be 1, 2, 7, 0. Oops, not good. It's not sorted. All right? So what's going to happen is we're going to get something like this. I still got 1, 2, 7 over here. And this part here, the first minimum will be 0, and then 3, and then 4. So 0, 3, and 4. And this will be what we claim is sorted in the hybrid sorting algorithm. Apparently, the result over here is not sorted because 1, 2, 7, 0, 3, 4, apparently it's not. All right? So this algorithm doesn't work all the time. I just show you one witness that it doesn't work all the time. Can anybody somehow sense what kind of structure, if I can say that that structure is satisfied for the array, then this hybrid algorithm can work? I'm going to show you the formal way, very precise, but can anybody give us some intuitive idea? What kind of input array structure is going to guarantee this hybrid method here is going to work? Go ahead.
So like the smaller elements are in the first half and the bigger elements are in the second half.
Okay, pretty good. I think that's already on a very good track. So the kind of the smaller elements are on the first half and the bigger element on the second half. Okay, one example up here. That's pretty good. But we want to make it formal. Okay. I will give you one example here. You guys can check it out. The working input over here is going to be, for example, I got 2, 0, 1, and also I got 4, 7, 3. For example, right? So if you think about it, this particular half and this particular half, oh, let me be a little bit better. This is the first half, this is the second half. Every element in the first half is less than or equal to every element in the second half. This kind of structure can guarantee this hybrid algorithm will work. If you can guarantee that it's a precondition, then this will work. No problem. All right, I will let you convince yourself why this is going to work, right? I'll let you do that. But now, how can we formulate this condition here? That's what I would expect you to write in the part C. How do we formulate that? I just don't want just description. I want something that's mathematical. All right, 1019, predicate logic, universal quantification. All right, let's now write it down. I'll write it down, and you guys think about it. And I'm just going to write it here. So let's say this is, I'll put a star here. This is the precondition. Precondition means it is something that the algorithm can assume to be true in order for that to work. All right? I'm going to use a single quantification, universal. I need two loop counters, I and j. The idea will be if I visualize the array as something like this, cut it into half. Let's say the first half and also the second half. If I randomly pick one element from here of index I, pick one element here from index j, I and j here. So it's guaranteed any element from here should be less than or equal to any element from here. That's what I want to express. How do we do that in math? Very simply. Right? I'm going to specify the range for I and j. I should be in this particular first half, and j should be in this half. So I'm going to say here, 0 less than or equal to I, less than n divided by 2. Again, we assume n is an even number, just to make it a little bit easier. Or we can take a floor or ceiling, whatever. And also n divided by 2 less than or equal to j, less than n. Input array, let's say the array is called input. I should be less than or equal to input of j. All right, so that's the assumption we have to make for part C in order for this hybrid algorithm to work. Right, so there are three parts for this particular problem here. I can see there's not a single line of code that we have to consider. But we already have covered quite many kind of interesting stuff for some variance to the or combination of two existing sorting algorithms. All right, any question about this one? Yeah?
So like for the logic, can we take, for example, like a middle value as a reference element and then develop the logic that all the elements...
When you talk about meta variable, why don't you show me what you really meant after class? We'll take a look. And then if I can share with the class next time, I'll share. That might be a little bit easier. Okay? All right, final call. Any question about this? this will be something the style you can kind of expect from the final exam. We don't necessarily just ask you to trace the code or just ask you something very straightforward. You got to think, right? Yeah.
The J, how it's like greater than or equal to n over 2 and less than n. Because aren't we starting from a new array? Aren't we starting from a new array with J?
So we're basically saying, given any array as the input. So we want to make sure there's certain structure that should be satisfied. Oh, okay. So we only got one array, by the way. We don't create any new array, right, for the sorting. We always work on the same array. We want to make sure even before we start sorting using this new algorithm, the input array must be something like this. Yeah, it must be something like this. All right, guys, think about it. And then if I can come up with more or inspire more by you guys about new problems, I will share. All right? Oh, Ben, you're here. Okay, makes sense, right?
Yes.
Okay, good. I think it benefits everybody. That's good. All right, let's now move on to singly linked list. That will be the important stuff for today. We'll see how much we can cover. Okay, so if you look at the slides, it's going to be starting from slide number 10. Okay, and to begin with, let's now recap very quickly. So think about arrays and linked lists. There are two fundamental building blocks for your algorithm. So we talked about arrays already. The most important aspect you want to remember about array is anything just involved about indexing. Maybe you want to indexing into a particular element will change something in that particular index for the array. It's going to be a very efficient operation, constant. On the other hand, whenever you actually want to do anything to do with the inserting in the middle, at the front, you will involve certain shift of the array. That's going to be costly, at least linear. That's something we want to remember. Most of the cases, whatever that's kind of efficient for the array, it will be efficient. Let me say it again. Whatever that's costly for the array, it will be efficient for linked lists and vice versa. That's an interesting aspect you can remember. All right, but we're going to see in very much detail. So today, I want to focus more on the visual level, but that will give you enough hints about how you can design algorithm for singly linked lists. My advice right at the front would be, when you try to design algorithm for singly linked lists for assignments or for your programming test, you definitely want to visualize what's really happening and what's being required. Simply thinking about how things will work in your brain is not going to lead you for too long. It's just difficult. It's not natural. You got to really think about the link structure on the paper. Okay, we'll see. All right, so let's now go over some important points about singly linked lists, and we'll do some visualization. Okay, linked list is simply a series of connected nodes forming a linear sequence, right? I'll talk about different terms over here. Let's go one by one, all right? The first thing to understand will be, we talk about singly linked lists for now. And hopefully today and Thursday, we can finish most of the singly linked lists. And before the reading week, we can definitely finish the doubly linked list. That'll be another extension, but we'll get there, okay? But for your programming test number 1, it's going to cover just singly linked list. Okay. A chain of connected nodes, right? By using aliasing. Aliasing is what we assume from 2030, right? What you learned about OO, but I'll review a little bit whenever necessary. Let's now, first of all, visualize what I really meant by connected nodes. Okay. Every node is going to look something like this. Think about it's more like a box with 2 compartments. Each one of them has some reference, like an address, that's going to refer to something else. For now, let's make some simple assumption. The first compartment is going to store something called data, or sometimes it's something called element. I'll stick to data just for now. Okay? And let's assume that every data item will just be a string. Just make it easy. Right? String is also an object in Java. And then the second reference over here is important. That's how we made the connection happen. That one there is going to point to another node, right? It's so-called a next reference. Okay. The next reference over here, the simplest case would be is simply pointing to now because it's a reference. Or it might simply point to a chain of nodes and etc. Okay, let's see some example. So let's say this one here simply points to another node over here. And then I will call this, again, 2 compartments. So let's say we got another data, let's say Alan Mark. And that one there points to another node over here. Let's just get one more. That will be another node over here, which points to data and also the next. Alan, Mark, and Tom. All right, and this one here will be null. Right, so this is an example chain of nodes with 3 nodes. Okay, and for convenience, you can somehow refer to, well, when you first create a node, you might just give it a name. Let's say n for now. Okay, just n. And the way you create a node just by calling the constructor, which you will see later today. But for now, let's stick to without a code. And for aliasing over here, it's really just about having multiple expressions referring to the same objects. That's about aliasing, right? So you got multiple expressions referring to the same objects. Just see one example right away. Let's say this node over here is called n, and let's say this node over here is called m. Right? And if I somehow want to refer to this particular node objects, I got more than one expression that can help me get there. I can either say n, which will give me these objects, or I can say n dot next. That will be another expression here, right? That's something you want to get very much used to for the singly linked list. So for this one here, I can say, for example, m over here, right? Remember equal in Java, right? The same address. n dot next. Let's play with this chain of nodes already. So I'm going to write several numeration here. So when I say n here, it's really referring to this node. We call that the first node in the chain. And then when we say n.data, n.data is referring to Alan. Or you can say that's simply the same address as Alan. Right? That's the information we know about the first node. Let's move on. And also we can say n.next. First of all, n.next is not referring to something that's null. So we can say it's not equal to null, right? Not equal to null. And also we can say n.next dot data will be, so n.next dot data will be Mark. Right, you kind of see the idea, right? Let's now give you some tests over here. What if I say n.next, next, next, dot data? If I try to evaluate this expression here at the runtime with that particular chain of nodes, what's going to happen? Yeah, Diego, go ahead.
Null pointer exception.
Null pointer exception, exactly. Simply because that's important. Guys, I can tell you that this will be your best friend in the programming assignment and programming test 1. You're going to write into this quite often. Null pointer exception. You want to avoid that as much as possible. All right. First of all, you can see n.next. According to the diagram, n.next is exactly null. How can you invoke data on null? Right? Null pointer exception. This part over here is simply null. So overall, if you try to evaluate this expression here, right, we got null pointer exception, right? When you try to manipulate the array the ones you write into more often will be array index out of bound exception. But when you try to work with linked list, null pointer exception will be more often. Okay. All right. And there is something about, okay, so we got, I think this is good for now. And let's talk about something about linear versus nonlinear. And then before that, each node contains the data and also the next, right? That's something we spoke about already. That's about the structure. That means each one of them will be some attributes you have to declare in Java. Okay, let's talk about linear versus nonlinear, which is also a very important distinction for you to understand. Okay, I'll start a new page. There we go. Okay. So we talk about linear versus nonlinear collections. Which we have to study both in this course, but linear first. Let's see definition. Whenever we talk about a collection being linear, like a linked list or array, so these are the two typical examples. That means each position in the collection, which can be an array, which can be a linked list, has a unique successor. Okay, let me write it down first. Each position in the collection has a unique successor. So the word unique is really the key word over here. Got to be unique. And of course, in the case of nonlinear, it will be not unique, multiple. Let's visualize in both array and also linked list. They are both linear. Let's say the case of the array. So if you consider array A in general, let's say that's your array over here, right? Index 0, and then you got all the way to somewhere in the middle, let's say index I, and also index I plus 1. So these two are the adjacent elements, right? Relative to this particular element at index I. The element at index I plus 1 is its unique successor, all right? Just one. Unique successor of 8 at index I, right? That element. Pretty straightforward. What about in the case of linked lists? Very similar. So if I also try to draw the linked list again, so I have some reference to, let's say, the first node in the chain. And let me just omit the data field just for now. All right. So let's say the next reference here, and the next reference over here, and etc. Can be as long as necessary. If I look at, let's say, this one here. Let's say this node here is called N. This node here is called N when I first created them. So we say that node N is the unique successor of N because it's only a single next reference for me to get there. I cannot get to another node. I cannot get to multiple nodes at the same time using the next reference. So think about, I can highlight just this next reference right here. Okay, this tells me that N is the unique successor of N. All right, again, unique. Unique, unique. All right, hopefully it makes sense so far. What about nonlinear? Nonlinear is something we're going to touch upon also very much when we talk about trees. Tree is a typical structure for nonlinear. Another example will be graph, which we don't really cover in this course. That'll be in 3101. But let's just talk about trees, just give you some intuition. So for nonlinear over here, the definition is going to relax the constraint on unique successor. It can be multiple successor. Doesn't need to be unique. Each position has multiple successor. Okay, right here. Let's visualize one tree very quickly. And there will be a particular tree that we're going to study called binary tree. There's also something called general tree, but let's not worry about it. Let's look at binary tree, which you have seen somehow when we talk about recursion tracing. So for that one there, let me talk about just binary tree, which is nonlinear. So you can start with one node over here. And typically, when we actually try to draw the tree, which is nonlinear, rather than drawing horizontally, like array and linked list, we try to draw vertically, right? That's something we get used to once we get to the subjects. There will be 3 compartments, typically, rather than 2 compartments. So there will be, you can think about the middle part is going to point to maybe some data element, like a string. But this one here and this one here will be how we can reach out to other nodes or positions in the nonlinear collection. And typically for binary tree, it will be called left and also right. And once we get there, you can see for this node here, you can also get to the left and also get to the right, and etc. So that one really branches out very differently from just array or linked list. Right? You can think about these 2 nodes are the multiple successor of maybe n. Okay? Not unique. All right, multiple here. All right, is it clear about linear versus nonlinear? Very important, actually. Well, I'll revisit this again once we get to the tree. Okay? And of course, for both linear and nonlinear collections, you can run recursion on both possibility. Arguably, when you run recursion on the nonlinear structure, it requires a little bit more sophisticated thinking, which you guys will do in assignment number 3 and 4. So you get enough chance to practice. Okay, we'll get there. All right, so that's about linear versus nonlinear. And then let me see what else. Okay. Also, I got something called head and tail. That one's kind of straightforward to illustrate. Basically, we got the very first node. Sometimes we also refer to it as head. And also here, we also refer to it. Let me use a different color just to show to you. But exactly where to define the attributes of head and tail, we're going to see. But for now, just understand conceptually. If there might be a way for you to refer to the very first node in the chain, we'll call that the head. There's another way maybe to refer to it at the last, called tail, head and tail, which definitely makes sense from the name. All right. And let's now move back to the slides a bit, and then we'll talk about something else. Okay, we'll talk about linear versus nonlinear, and also we'll talk about aliasing. We'll see more example as we go. And then each node has the data objects and next node, right? We already covered them. All right, that's why it's important. Relative versus absolute indexing of the 2 data structure. All right, so that's something we also got to talk about. And to get some intuition about the running time as well. Okay, let's now talk about this one here. For array, it's always absolute indexing. Meaning that you got to give some specific integer telling you where you want to get into. Absolute indexing of arrays, which we know pretty well, but I'm going to put it here anyway so you can compare. So when we talk about the absolute indexing, that one there is a very cheap operation, constant operation. That one we already know. Let's just review very quickly. Whenever I got array A, and then I got I. For those of you who took 2031 or 2032, right? We know that the A here indicating the starting point of the consecutive block in the memory about the array, right? Starting address of the array. Whereas the I over here is more about for the underlying compiler to really calculate the offset of the address from the starting point, right? So the calculation of that address is a very efficient operation to do. So that's the main point. Okay? So this will be some integer expression which indicates about calculating the address offset from A, which is the starting point. Right? That's something we know from the other course. And that one there is simply just big O of 1. All right. That's about absolute indexing for the array. What about relative? Relative is the nature of singly linked lists, or linked lists in general. Let's see exactly how that can be understood. So we talk about relative positioning, let's say, of linked list. So here, when I say linked list over here, it definitely includes the possibility of singly linked, but also doubly linked, the same. Okay? And we talk about relative. Relative here, I can tell you also right away, it turns out to be more expensive than absolute. It's going to be big O of n in the worst case, but we're going to see exactly how. All right? Let's now draw a chain of nodes again, and we'll go from there. So let's say I have the head of the chain of nodes, this node over here. And again, let's omit the data, right? Just focus on the next reference. Next, over here. Next, over here. And also next, over here. And then until I hit the null. All right. So when we talk about relative over here, it's really about the next reference we are using. So think about we got the next over here, the next over here, and the next over here. And potentially, we also got to check for null. That's kind of the special case, right? So all these are the mechanism for relative positioning, meaning that given maybe the head of the list, you have no idea what's really the node more than one node ahead of you. The best you can do is to go for a single next reference lookup. Go to the next node. From there, the best you can do is do another single next reference lookup and etc. There's no way for you to really jump to a particular position right away. There's no way to do that efficiently, like in array. In a linked list, the best you can do is keep using the next reference to where you want to go. That's a very important mechanism to really notice that works naturally for a linked list. All right, so here I'm just going to put it over here. So this will be the mechanism for the next reference, right? So this will be the next, this will be the next, and also the next. So this will be for relative positioning. Because the only thing you can go to will be the unique successor for that particular node. So now, why do I say that relative positioning is actually inefficient? It's because sometimes you cannot avoid that. You have to go to a particular position in the chain of nodes. So we can somehow simulate absolute indexing using relative positioning. That's where the complication comes from. All right. So what I want to do is I want to now think about the chain of nodes also has indices. We got 0 here, 1 here, 2 here, 3 here, just like array. And of course, you cannot simply say, let's say I got some list variable. If I got a list variable L, I cannot just do something like this. I cannot. It's not supported in Java, right? The square brackets notation is only reserved for array. So the best we can do is to support maybe some method that we're going to implement ourselves, which we'll see next time. So if I say L dot, let's say get, and I want to give some input value I. And I here potentially can be 0, can be 1, can be 2, can be 3, etc., as long as it's valid, right? So we are basically trying to simulate absolute indexing like array. But how it's going to work behind the scene is going to use the next reference. But why is this inefficient? You got to think about what would be the worst case. The worst case would be when I value gets very large, right? So if you think about I over here, the worst case would be I gets close to the size of the chain, which we say n, about input size. You might be thinking, what if I already put, let's say, tail over here? In that way, accessing to the n will be constant. I agree for that case. But what if I say maybe n divided by 2? Right? If I give you I being that value, you will still require n divided by 2 next reference lookup to really get to. If I want to get to position 2, that will require 1 next and 1 next all the way from the head. You got to start from the beginning. 1 next and 1 next to get to position 2. You need 3 next to get to the third position over here, and etc. So now if I give you something very close to n, how many next reference lookup do you need? Close to n. So that's going to be linear. Right? So that's kind of intuition you want to think about. All right, close to the size of the chain n. So now this will be roughly equal to the number of next reference lookup. Okay, close to n, linear. All right, in summary, you want to be very clear about between absolute indexing and also relative positioning in the two different structure, right? And whenever you want to get to a particular position in the linked list, it cannot be efficient. You have no way around, but you have to start from the head and go all the way there by using a number of next references corresponding to which position you want to get to. Okay. Question about this? All right, I hope that's also clear. Okay, let's now move on. We'll see some nice illustration about different operations you can perform in just one moment, very quick. I just will have a few things to say about the linked list. Okay, let's see. All right, if you go back to the slides, what we have is we got, okay, relative versus absolute, and also we got, oh, this one here, easy to see. What is so special? Let's say let's say this is a chain of nodes over here. This is the last node. And these nodes are the rest of the list. What is so special about this particular node? What do you see as a difference? That's outstanding. No next, exactly. All right. So the last node is the only node where the next reference will be null. And this is a very important fact for you to be aware. Typically, if you want to run a loop to iterate through the linked list, you want to say, I want to go all the way until the next reference gives me null. That can guarantee termination of your loop. Right? That's also something we'll see. So this is the last node, for which I know the next will just be equal to null. Okay, very important. Okay. Okay. Let me go back here. All right. And let's now talk about this very important point. Okay. Oh, by the way, I already talked about head and tail, right? So that one is already there. And here we talk about the chain structure. There is not a fixed length about how long the chain should be. As long as your memory can really accommodate, it can be as long as you like. So there's no fixed length. So when you first create a linked list, you don't need to specify the length of the list. All right? Start with empty, basically. And let's now spend the next 10 or 15 minutes on this particular part, about how the list may grow dynamically. All right? Let's talk about that. So that'll be the most important part for the introduction here. All right? So we're going to do this visually, but somehow you can also see some intuition about how the code is going to be written I'll write some like a fragment of Java code as well, right? We're going to talk about 6 different scenarios. Let's say I got this existing chain of nodes. We got a head, we got a tail, and we got 1, 2, 3, 4, 4 nodes in the chain already. So if I want to insert some new node into the chain, I can choose to insert maybe in the beginning, in the middle, or at the end. We're going to see how to perform them and talk a little bit about the running time conceptually. Okay? We're going to see the Java code a little bit later. Let's start with the first one. Let's say I want to insert a new node storing, let's say, Toronto into the beginning. Okay? Let's do the first one. Toronto over here. And then I want to insert that into the beginning. All right, for the first one, I'll just show you right away, but you will see the idea. In order to insert a new node, first of all, I got to create a node. Let me create this node over here. Let's call that new node just T for Toronto. And for the data part, I will just put the data right here, right? Toronto. That will be step number 1. And in the beginning, the reference to the next will be just null. Step number 1, create a new node first. I want to insert this new node here as the first node in the chain. What does that mean? That means the head, rather than here, is going to point to here. And then this node that used to be the first node is now going to become a second node, because the new first node is now going to point to its next to it. Right? That's kind of the updates you have to write. And let's see how to do that. We need another 2 steps. Step number 2. Rather than this part here pointing to null, I want to let it point to the existing head. To write a Java code, very easy. I can simply say t.next is assigned to the existing head. Right? And the third step, the head over here has to be updated. It should not be pointing to here anymore, because this one should be a new head. Right? So head, rather than pointing to over here, is now going to point to over here. So you can think about the head is assigned to just T. That'll be step number 3. So we got 3 steps in total to insert to the first. 1, 2, and 3. All right, questions about inserting to the first? All right, let's say insert into the middle. Let's say I have Vancouver here. I want to create a new node, but I want to insert into the middle. So for the middle here, there are different variants. Let me just talk about one of them, the easier one. Let's say you're implementing a method that's going to insert this new node into the middle. Let's say I already know which node I'm going to insert after already, let's say. Let's say this node over here is given as input, its reference. Let me call it n. So this one here is assumed to be the input. Another variant might be I want to insert a node into a particular index I. That will be simulating absolute indexing in the linked list, which we know is not going to be efficient. Right? That's something we'll get into a little bit later. But for now, how can we do this one here? Well, diagrammatically, you want to create a new node over here, and then make sure, rather than this n here pointing to next, like that, it's going to point to here. And then the next of this is now going to point to over here. That's basically what you got to do, right? But how do we do that in Java code, right? You got to make sure the steps you specify will do exactly that. So what we do is we're going to first of all, step number 1. We're going to create that new node. And that new node, let's call that Vancouver. In the beginning, pointing to null as a next. And let's call that node V. That'll be the first step. Now, what about the remaining part? Somehow we want to make sure this will point to here and this will point to here. All right? So the second step, we can try to fix, rather than pointing to here, we can just point to here. Any suggestion about what we should really write? Say it again, please. A little bit louder. Yeah. V dot next. Yep. Thank you so much. Equals n dot next. Exactly right. Okay. So we are saying that V dot next, rather than pointing to here, is now going to point to this node here, which can be specified as n dot next, which is this node. Right? This kind of a visualization and translating that into Java is exactly what you got to do in the assignment number 2 and in the programming test. Okay. Okay, that's second step. And the third step, we got to fix this pointer here. Right? You got to make sure this n dot next is not here anymore. It should be pointing to here. That part should be easy. So this one here is going to be pointing to this one here. So n dot next is assigned to v. That'll be number 3. So we got 1 here, 2 here, and 3 here. 3. Inserting into the middle. All right. And let's now do inserting to the last. Montreal to the end. Right, we still need to create a new node. No way around. So the first step, let's now create that first new node, which is going to be Montreal over here, and then pointing to now in the beginning. Right, conceptually, we want to make sure this one here now is going to point to over here. Right, agree? And then we want to make sure the tail is now has become this new node. That's it. Okay. So let's try that. Step number 1 is already done. Let's call this M. And step number 2, we want to make sure this old tail is now going to become the second last node in the chain. So now it's next, rather than now, it's now going to point to here, right? So now it's going to point to here. So we say that tail the next assigned to n, number 2. All right. And what about number 3? You're going to change the tail over here and let it point to this new node. Number 3, the tail is assigned to just m. All right, so we got 1, 2, and 3. 1, 2, and 3. And some very important exercise for you to think about. For all the 3 operations that we have spoken about, the first step is always about creating the new node. And now for number 2 and number 3, can we swap them? All right? I'll put that as an exercise over here. You want to think about it. If you swap them, well, what's going to be the consequence? You want to know exactly how to change the diagram and know what the consequence is. Swap 2 and 3. For example, let's say if I want to insert Toronto as a head, as a new head, I'll create the first node still, but I'm going to do this one first, second step. And then I'll do this one as a third step. What's going to be the consequence? Is it going to be something I still expect or something else? Right? That's exercise for you. So that will be what I consider 20-30 level tracing question. Right? You got to make sure you know how to do it. All right, let's talk about removing. Right, I'm going to do 2 of them just to give you intuition about removing, which will be slightly more complicated than inserting. And then for the final one, I'm going to give you a little bit hints with the exercise for you. Okay, let's do that quickly. Let's say I want to remove the Los Angeles over here. Okay, I want to remove this node here. Well, diagrammatically, if I want to remove this node, it's not too bad. Remove it, you got to set this reference here to be null. So it's not pointing to it. So once you set this reference to be null, this node here will be isolated. So hopefully it will be garbage collected automatically by Java virtual machine at some point. At the same time, the head over here is going to point to what used to be the second node. Right? But if you want to implement this, you might need some additional variable to help you. I can tell you right away. You can think about if you can get rid of the variable, but you may not be able to. All right, so let's now go over that. So step number 1, I'm going to introduce a new node variable called temporary. Temporary is just going to be an alias for the head. What does that mean? That means the temp is just going to point to wherever head is pointing to. First of all, let's start with that. All right, it's going to be useful, as you will see. And the second step is going to be, I want to change the head. Head, rather than pointing to over here, is now going to point to over here, the second node, because I'm going to remove the first one. And this one here, I'm going to write something here. Hopefully that wouldn't seem too strange to you. I'm going to say something like head is going to be assigned to head the next. Right? That's also something you're going to write quite often to update the reference. So the head over here is going to be updated by the right-hand side. The right-hand side is the head dot next, which is this node here. I want to reassign that to over here. Okay, step number 2. And step number 3, you can see at this point here, I already lost the reference that's used to point to this node here. But I still want to make sure I can assign this one to be null. But I got a temporary variable. That's why I need it. All right. So step number 3, get rid of this. And so this one here will be temp is simply assigned to null. So these are the 1, 2, and 3 steps. We're essentially writing the code, right? But you can see in a way, we are tracing at the same time. Let's do one more, and then I'll give you the exercise. Let's say we want to remove from the middle. Let's say I want to remove Atlanta right here. All right? I want to remove it from the middle. Oh, Los Angeles, of course, is from the beginning. All right? From the middle. Diagrammatically, if I want to get rid of this node, what's going to happen is here I'm going to set a pointer right to over here and get rid of this pointer. That's what I'm going to do, right? How do I do that? All right. So there will be 2 steps necessary. But before that, it's more important to talk about 2 inputs, which I assume. Let's say we assume there are 2 inputs. Let's say this is the node I want to remove. But the problem is, I want to remove this node, but I also need to set the next reference of its previous node, as you can see. But the problem is there's no previous reference for singly linked list. Remember, there's only next reference. So there are 2 ways to go with this. Let's try the easier way today. Let's say as part of the algorithm input, I will give you that previous reference. I'll give that to you. So that will be very efficient because you're given. You don't need to spend any efforts calculating it. But approach number 2, which we'll see next time. In general, when you are given the algorithm to really implement to say, I want to remove just this node in a singly linked list, in order for you to really get a previous, you have to really run a loop to say, I go from the beginning of the chain, go all the way until the node whose next is the node I want to remove. So I can calculate the previous. That's something we'll get into a little bit more next time. And calculating the previous, again, can be linear, because if n is very close to the end, in that way, calculating the previous will be just like a linear. All right. So for now, I'm just going to give that to you as the previous. All right. You can see, obviously, previous.next is just equal to n. Right? Let's say we're given these 2 inputs. Let's say. If we're given these 2 inputs, how should we implement them? Okay. Step number 1. I want to basically say, change this reference over here, and then put it here. All right, so for that part, what should I write? previous dot next, which previous dot next, which used to be pointing to this node, but that one's going to be removed. I'm going to change this pointer here and let it point to what used to be the n dot next. That's what I will do. All right? Equals n dot next. Let me pause for just one moment. This will be one way to write for achieving step number 1 by changing the pointer. Is there any way for me to write this expression here differently? You mean the tail here? But I understand that, so somehow I agree this one here happened to be the tail, but in general it may not be. Good thinking. Specific to example, you're right. This will be the tail, but there might be more nodes in general after that. So I want something different. Yes, brilliant. That's exactly right. Right, guys? You just get to see the diagram and work out the solution, right? And this one here, alternatively, you can say previous dot next, which guarantee to be n. And then dot next. This will also work. All right, step number 1. And step number 2, we're just going to remove this reference over here. All right, step number 2 will be n dot next equals null. So we got 1 here, 2 here. 2 steps only. All right, the final one, which will be exercise for you. You want to think about if I want to remove the last node in the list. Let's say I want to remove the node at the end. Let's say this guy over here. We are facing a similar challenge as the previous one. Because conceptually, if I want to remove this node over here, what should I set a tail to? Previous. I don't have a previous in general in singly linked list. So in order for me to really get to the previous, either the previous is given or I need to calculate a previous. All right? Let's say you're given. Let's say you're given this particular reference over here. I will call that SL, second last. So for this algorithm here, you're given a second last node reference. How would you remove the n? Think about the steps. All right? So for this one here, it will be exercise for you. Given SL, second last, you want to remove the last node. All right? All right, important for you to see. All right? All right, any question about these operations? We kind of gone through all the basic ones that are kind of necessary for singly linked lists. Next time, we're not done yet for today, not yet, but next time we're going to look at some of them in coding and analyze a little bit more about running time, seeing the code. But you can already kind of imagine what the running time might be for each one of them. Question, quickly.
Here, like the times we point it to null, right? But couldn't you just do n equals n dot next and the garbage collector wouldn't just know that there's no pointer to the object?
Sorry, which one are you talking about?
Deleting the first print orange?
If you got alternative implementation, let's talk about it after class. So it will take more time. All right, good. But what I suggested would maybe one possible solution. But if you got something else, feel free, and we can discuss. Okay. Alrighty, so I would suggest we take a very short break, and then I'll go over a little bit of Java code with you, and then we'll continue next time. Okay, so just take a 2 minutes break and take attendance at the same time. All right, before we call it a night, I will just want to go over Java classes with you. So these are pretty much what you will be given for the assignments and also the programming test as a starter code. That's something you don't have to build from scratch, more or less. But let's go over them very quickly, 4 minutes. So there will be 2 classes. We'll talk about the level of each individual nodes and also individual list. All right, let's talk about them. When we talk about node over here, you can see that's a type, okay? Individual node. And you will see we got 2 attributes there. We got elements and also we got next. And notice that the next node has the same type as the class itself. Right? I'm pretty sure I've seen something like this. Formally, it's something called recursive type. Just like you call a method recursive if you call itself. Now you call a type recursive if it's referring to the same class where it is defined. Okay, recursive type. And whenever you try to visualize a node, which we have already seen, but let me just do it again. So let's say I got some node object over here. I'll put a class name here. And then we got elements or data. Usually we just get element or data. Let's say element. Element and next. Right, over here. And the element, let's say string, is string in this case. My point to some string over here. And also this will be the reference of some node in the chain. Right, and also we might give the name of the node, for example, n, when we first create that. Right, that's a node. You can instantiate as many nodes as necessary. Right, you can see the constructor here for the node will be taking the string elements and also the next node reference. So n here is going to be assigned to the next reference. Okay, so this will be the next of that particular node. And also we got very straightforward accessor for the elements and next, and mutator for the two attributes. Very straightforward. And the second class we're going to worry about will be something called singly linked list. So that'll be at the list level. For now, we assume there's only one attribute there, only one, the head. And notice that the head over there has the type node. That's how we draw the connection between the two classes. Oh, sorry, right here. Right here. All right. How do we visualize that very quickly? At the runtime, you only create, let's say, create one singly linked list class, like objects. So what you will get is something like this. I have an object right here, and let's call that singly linked list. Singly linked list. And for now, just one attribute is called head. And then let's say this one may be called maybe L for list. In the beginning, head will just be null. That means we got an empty list. How can I somehow connect some list of chain into the list? That's how I do it. So what I need to write will be something like, I can say L.head is assigned to just n. That will make sure this one is now going to point to n here. But again, we got aliasing. You can see L.head now equals n, right? And what about the methods there? We'll talk about set head, which is pretty much what this is doing. And then we'll talk about how we can compute the size, tail, at first in a different operation as we go for a linked list operation. 10 seconds, okay. So review this class structure very quickly. And then before Thursday, your assignment number 2 will be released as well. Take a look, and then we'll continue on Thursday.